Alright, so this is our final video for Math 1560 Calculus 1 at U of L for fall 2017. And in this last video we're going to look at one application of integration. It's not that applied, it's an application to another math problem. We're going to use integration to compute area between curves. So remember that area was the original motivation for defining the integral in the first place. If we're given a positive function, or at least a non-negative function, right, then we think about the area that lies between the graph and the x-axis. From a to b, this is what we think of as the integral. And even in the case where the function isn't positive everywhere, we sort of take the area that lies above the x-axis, we subtract the area that lies below, and that still gives us the integral in that case, right? So we think of integrals in terms of area, and this is, you know, what you should always have in mind when you're calculating integrals. Remember that you're computing areas, and so sometimes there are certain functions where this interpretation in terms of area makes things a little bit easier. Think about this example here. If we were to graph this function, okay, if I were to graph, well, let's first graph the original function. Y equals, if I graph y equals 2x minus 2, I get that. But I'm interested in the absolute value of this thing between 0 and 1, right, which is, say, about right there. Let's say, or sorry, between 0 and 2, right? There's 1, there's 2. So what happens when I take the absolute value? Well, this part, which is this part remains the same because that's already positive. It's above the x-axis. Anything that's negative gets flipped around and gets flipped like that, right? Okay, and so now we can see, once we take the absolute value, we get the area under this blue curve. So there's sort of an area 1, there's an area 2, and you notice that both of those areas are triangles, and in fact, notice that the absolute value of 2 times 0 minus 2 is 2. The absolute value of 2 times 2 minus 2 is also 2, and so area 1 half, the base is 1, the height is 2, is 1, area 2, 1 half, base times height. All right, so both areas are 1, so the total area, you know, we expect that this integral should come out to give us 2. How do you see that directly? Well, one way to see this directly, if we didn't have the picture in front of us, or if the function was more complicated and we couldn't just write things down, is to say, hey, one of the properties of integrals that I have is that I can always split an integral up. So I could split it up like this, right? I could go from 0 to 1, and then I could go from 1 to 2. Okay. And then I could say, well, you know, I know just looking at the graph, or working with the absolute value function, right, I know that this is going to be equal to, well, the absolute value leaves, 2x minus 2. The absolute value is going to leave the input alone. It's going to leave that 2x minus 2 alone, as long as 2x minus 2 is bigger than 0. And 2x minus 2 is going to be bigger than or equal to 0 whenever x is bigger than or equal to 1. And it's going to be the negative of 2x minus 2, which is 2 minus 2x, whenever x is less than 1. So what we get is we get the integral from 0 to 1 of 2 minus 2x plus the integral from 1 to 2 of 2x minus 2. We split it up like that, right? Because we know the sign of 2x minus 2 on each of these subintervals, we can dispense with the absolute value. And now we can evaluate these integrals as usual, right? So this is going to be 2x minus x squared from 0 to 1. And then we get x squared minus 2x from 1 to 2. So we get 2 minus 1. And then we get, well, 2 squared, which is 4, So yeah, 2 squared is 4 minus 2 times 2, which is also 4. Subtract, and then we get, when I put in the lower limits, I get 1 minus 2. Okay, so 2 minus 1 plus 4 minus 4, we do get 1 here, and we get another 1 there. We do get that 2 that we expect for the integral. Okay, so I mentioned this integral involving absolute values because we'll see that when, in the very last slide, if you want to kind of look at the general procedure for finding area between curves, sometimes you're going to have to deal with these absolute values and you're going to have to split things up. We'll see what happens in a bit. Okay, so here's the general problem. F of x less than, g of x. Right, so we have two functions. F is less than g. We want to find the area of the region between them. So what this looks like is something like this. We've got maybe y equals g of x here, and we've got y equals f of x down here. Here's A, here's B, and we can see what the region we're interested in looks like. So you can work this out using the same sort of reasoning that we use to come up with the definition of the integral. You can partition your interval, so you can break it up into pieces, and we're going to approximate the area by rectangles. But now notice, how do we calculate the height of a rectangle? Well, if I choose a point, and let's just do it for one rectangle, I choose a point in one of my intervals, well, I can go up to the graph of g, I can go down to the graph of f, and I can construct a rectangle like so. And so what is the, so this is sort of AI. So what is the height of the rectangle? Well, it's the distance from the top to the bottom. It's given by g of ci minus f at ci, right? And then I multiply by delta x, right? And so you kind of go through the same process that you went through when you defined the integral. And you know, the only real difference there is that when we did the integral, the bottom function was just 0. We take the x-axis, we take 0. So now we're just changing where the bottom of that rectangle is. And so the only thing that we change is the height. And so what you end up with is that the area should be the integral from a to b of g of x minus f of x dx, right? So to get the y values, we take the difference between the two functions. That gives me the heights of the rectangles, and I do height times base for each of the rectangles, add them up, and I get to this area formula here. Okay, so that's our formula. Let's try putting it to use. Okay, equal sign. Apparently I have lots of typos in my very last video. It's always a good idea to sketch things so we know what we're dealing with. Okay, so here's y is equal to cos x, and here's y is equal to sine x, and this point of intersection actually happens at pi over 4, right? So we know that sine of pi over 4 and cos of pi over 4 are both equal to 1 over the square root of 2. Okay, now one of the reasons that you have to sketch things out is you got to know which curve is on top, right? So now we know that cosine is the curve on top, right? So that's the upper curve, right? And the formula is always kind of, it's always upper minus lower, right? We top curve minus bottom. So g of x in this case is cos x. Cos, I guess I called them f and g, did the other way around. But anyway, cosine is the curve on top, sine is the curve on the bottom, and so our area formula should be, well, we're going from 0 to pi over 4. We do upper minus lower. So cos x minus sine x dx. There's our integral, and so now we just do antiderivatives as usual. So we do the antiderivative for cos, which is sine. Antiderivative for minus sine is cos, and we evaluate from 0 to pi over 4. So we get sine pi over 4 plus cosine of pi over 4, subtract sine 0 plus cos 0. Okay, so that is 1 over root 2 plus 1 over root 2 minus 0 plus 1. So, and by the way, 1 over root 2, remember that this is the same thing as root 2 over 2. I've got two of them, so this is the square root of 2 minus 1. That gives me the area between those two curves. Okay, so that all makes sense, that works out, but there's, notice that if I had asked for the area, let's say going from, what if I wanted, let's say I want x to go from 0 to not pi over 4, but pi over 2. If I wanted to go all the way to pi over 2, right, which is going to be here, well then I want to include this area as well, right? But notice that between pi over 4 and pi over 2, right, the curves switch places. Now sine is on top, cosine is on the bottom. So when I do upper minus lower, I have to do sine minus cos rather than cos minus sine. The order changes. And notice that that's kind of the same thing that you're doing when we did the 2x minus 2, right? We could think of that, we could think of this differently. We could think of that as the area between the graphs y equals 2x and y equals 2, and depending on which one is on top, right, it's always upper minus lower, right? We notice that the order changes in the two regions because we want area to be positive, right? So we wouldn't want to just do cosine minus sine all the way from 0 to pi over 2. We would get the wrong answer because that second area would come with a negative sign. We want it to be positive if we're interested in total area, and so you have to account for that. Right. So there's a couple ways to think about this. You can think about splitting it up, right? You can find this point C where the two curves cross, right? So that's the point of intersection. And we find that, say, F is on top from A to C, G is on top from C to B, and so you split it up into two integrals, right? But another way to say that is that you're simply integrating the absolute value from A to B, and you're using the piecewise nature of that absolute value function, right? The absolute value of f of x minus g of x, right, by definition, it's f minus g whenever f of x is bigger than or equal to g of x, and it's g minus f whenever f of x is less than g of x. Right? And so the absolute value kind of accounts for this, it has it built in. So if I wanted to find this area here, right, if I wanted to find this area between y equals x and y equals x cubed, well, I guess the answer is simply the integral from minus 2 to 2, absolute value, x minus x cubed dx. But I want to be able to evaluate this, and if I want to be able to evaluate it, then I need to have some idea of what I'm looking at. So let's sketch things. So let's draw y equals x. Let's draw y equals x cubed. So the cube function is going to go something like that. So this is going to be at 1. This is going to be at minus 1. And of course, that's an intersection at 0, right? Right. So those points, if you're wondering where those points come from, I want to find out where the two curves intersect. So I say, when does x equal x cubed? Right. So I want x cubed minus x equals 0. X, and if I factor completely, I get down to here. And so I see that the points of intersection are when x equals 0, x equals 1, or x equals minus 1. Okay, so now I can see what I have to do. From -2 up to -1, which curve is on top? Well, from our graph, we can see that the cube function lies below the straight line when x is less than -1. So I have to go from -2 to -1, and I have to do x minus x cubed. X is on top from -2 to -1. Okay. Between -1 and 0, now notice that the red curve is on top. The cube function is on top. So from -1 to 0, the cubic function is on top. So I've got to do x cubed minus x. And then from 0 to 1, well, now the straight line is on top again. Y equals x is on top again. So from 0 to 1, I've got to do x minus x cubed. And finally, they cross one more time at 1. And from 1 up to 2, the cube function is on top. So I have to do x cubed minus x. So I've got to do those 4 integrals. I'm going to leave it, I think, for you guys to work out the details because I'm out of space, I'm out of time. You'll probably find that none of these integrals is all that hard to evaluate, and you might also be able to employ a certain amount of symmetry and realize that if you can calculate the value for this integral and that integral, well, these two integrals will be the same, these two integrals will be the same, and so I can just calculate the last 2 integrals, double that value, and that will give me the total. Should we do it? Can we do it? Let's do it quickly. Okay, so what do we get if we were to continue this? We get x squared over 2 minus x to the 4 over 4. I'm going to double the whole thing, and that's going to go from 0 to 1, and then I get x to the 4 over 4 minus x squared over 2 from 1 to 2. That's what we have to work out. Well, that's still not super nice, right? A half minus a quarter, what do I get? 2 times a quarter for the first one. 2 to the 4 is 16 over 4. So I get 16 over 4, 2 squared over 2, 4 over 2, subtract, and then I get a quarter minus a half. Okay, so 2 times, well, this is also going to be a quarter minus a quarter, so there's a half plus 4 minus 2. Okay, so that's 2 plus a half. I'm doubling it. I'm getting area 5. I did that in an awful hurry, so I might have made an arithmetic mistake, but you can feel free to double check my work and see if you get that same answer. Alright, that's everything that you need to know for the material in Math 1560 up to area between curves. That's the very last subject that you had to learn, so if you've covered the material up to now, whether you've watched the videos, read the textbook, done the homework, whatever way you chose to approach the course, if you've got to this point, you're hopefully ready for that final exam that's coming up.